Okay, welcome to Module 7 lecture. This is again on the Network Security Fundamental series, and tonight we will be talking about PKI and cryptographic protocols. So hopefully by the end of the module, you will be able to define digital certificates. You will be able to describe the components of PKI. You'll be able to describe the different cryptographic protocols and explain how to implement cryptography. So last week, we actually talked a lot about how the public key versus private key system is, and we definitely went a little bit deep into the definitions of the private key, but when it was about public key, we deferred it to this week and we said we're going to have more details to come, and this is making the promise happen. So first thing is, let's talk about digital certificates a little bit, right? One of the common applications of public key cryptography is digital certificates. Using digital certificates involves understanding of their purpose, knowing how they are managed, and determining which type of digital certificate is appropriate for a specific situation, right? So asymmetric cryptography, which is also called public key cryptography, uses a pair of related keys. The public key can be distributed and shared with anyone, while the corresponding private key must be kept confidential by the owner. And it can be used as a proof to verify a signature of the sender whenever you're actually sending a message. A degree of proof can be provided with asymmetric cryptography by creating a digital signature at the source, which is an electronic verification of the sender. After creating a document, sender basically generates a hash digest, and we discussed this last week. If you don't remember that, go back to that video and watch it, please. So as I said, the sender generates a hash digest on the document and then encrypts the digits, which his private key is being used in order to encrypt that, which then serves as a digital signature. Then the sender sends both the encrypted document and the digital signature to the receiver, who then decrypts the digital signature using the public key of the sender, revealing the digest. If the receiver cannot decrypt the digital signature, then the receiver knows that it did not come from the actual server, and the integrity of this communication is going to be voided. However, remember that a digital signature has multiple weaknesses, right? But before we go through the weaknesses, let's take a look at what I just explained for you. So if Bob in this example uses his own public key and decrypts a message, in this case, the message says buy a stock right now, and then sends it over the line, the receiver, which in this case is Alice, basically just needs to look at the Bob's private key and using the public key that he has, go ahead and decrypt the message. Now think about some middle guy, some imposter guy that basically is conducting a man-in-the-middle attack, is intercepting the message, right? And then change it. In this case, the integrity of the information transportation is going to be totally gone, right? In our example, we suppose Bob created a message along with a digital signature and sent it to Alice, right? However, Mallory, in this case, intercepted the message. Mallory then can create her own set of public and private keys using Bob's identity. In this case, Mallory could then create a new message, right? And a new digital signature with the imposter private key that she is going to create, and then send it to Alice. Upon receiving the message and digital signature, Alice, naive, doesn't know what happened, right? Would unknowingly retrieve the imposter public key, thinking that belongs to Bob, and then decrypt it. And then Alice would be tricked into thinking Bob had sent it then, which in this case, she's gonna go, I mean, she's gonna go ahead and sell the stock, which is not a good idea. So this is the problem that comes with the public key, because public key is actually published publicly. And for that reason, if the message can be intercepted, of course, it can be regenerated with the imposter key, and then your whole communication is not secure anymore. So several entities and technologies manage the digital certificates, which are the solution to this problem. So basically, if you think about the trust, right? If I trust one of you guys and you trust someone else, and that someone else trusts you, then me and that someone else can trust each other through the transitive trust through you. So if we can find a third party, that the third party can actually take care of the authentication of the sender and receiver, then the problem of a middleman coming into the problem and trying to intercept and manipulate the message is going to be out of the game, right? And there are multiple ways to do that, right? So as we said, multiple entities make up strong certificate management, including a certificate repository and a means for certificate revocation. So they can authorize the certificates, make sure it's authenticated. Then on top of it, they can keep certificates safe. And if need be, they can revoke it. Okay. So the scenario that we talked about before just shows you some of the entities that get involved in the digital certificates can fix the problem, right? A user who wants a digital certificate must generate the public and private keys to use and then complete a request with information such as their name, their email address, their physical address, I don't know, social security number, whatever, right? Bunch of information that helps authenticating them, and then submit this request, which is called certificate signing request, or a CSR. The user electronically signs the CSR by affixing a public key and then sending it to the registration authority, who is responsible for.
I take the silence as a no, I didn't, so.
Sorry, if you're not talking, please mute yourself. Yeah. So once that request is received, it's going to be verified, and then the CSR is going to be transferred into an intermediate certificate authority CA. The intermediate CA, of which there are many out there, and there are many entities that they can actually provide that service. They are going to be issuing the digital certificate, and they're going to be responsible for the digital certificate. So intermediate CAs are subordinate entities designed to handle specific CA tasks, such as processing certificate requests, verifying the identity of the individual, and such. Depending on the type of digital certificate, the person requesting a digital certificate can be authenticated in multiple ways. So the person can just be authenticated through an email, right? And this is the simplest form. The owner might be identified only by an email address. Although this type of digital certificate might be sufficient for basic email communication, it is not sufficient for the most other activities, because you're not going to know the person who is sending you the email is the person that they actually claim to be, right? The other way is maybe through a document, right? A registration authority can confirm the authenticity of the person requesting the digital certificate by requiring a specific documentation. Let's say, I don't know, let's say a passport, right? Or a copy of employee badge, or a school ID, or some kind of document that can prove you are who you say you are. And then finally, the most effective one, and at the same time, the least efficient one, is in person. So in some instances, the registration authority might require the applicant to apply in person to prove their existence and identity by providing government issued passport or I don't know, their driver license or their VA card or anything like that, right? So no matter which one you're looking at, the whole idea is these CAs are authenticating the sender and the fact that the sender is who they are claiming to be, right? Just just exactly as a breach at the, let's say, DMV office could result in many fraudulent card titles being distributed and issued, or many fraudulent California IDs being issued, right? So too, a compromised CA can turn into a certification issuing entity that is issuing fraudulent certificates. So one of the attacks that is very common is attack on a CA. And this certificate authority, after being compromised, can compromise the security and the encryption power of almost everyone who has been working with them. A common method to ensure the security and integrity of a CA is to keep it in an offline state from the network, which in this case, we call it an offline CA. It is only brought online, which in that case, we call it online CA, when needed for a specific and infrequent tasks, typically limited to the issuance or reissuance or revoking of the certification, and also authorizing the intermediate CAs. Otherwise, we're going to keep the CA offline. Of course, this by itself is going to bring some complications into the game, which we're going to talk about it later down the road. So multiple entities make up strong certificate management, including a certificate repository and a means for certificate revocation, as we discussed. So a certificate repository is a publicly accessible centralized directory of digital certificates that can be used to view the status of digital certificate. The directory can be managed locally by setting it up as a strong area that is connected to the CA server. So this storage area that is connected to the CA server is going to be the repository that you're looking at. And here the issue is you have to make sure this storage area is secure, right? That's another concern when it comes to the public key encryption. So the digital certificates normally have an expiration date. However, in some circumstances, the certificates are revoked before their expiration date even arrive. Some reasons that you may think are like a certificate is no longer used. Let's say if a user is not using their certificate for a certain period of time and the certificate is so-called idle, it can be revoked, right? Sometimes when a data is changing, like user's address, their physical address, their email address, or anything like that changes, in that case, you're going to have the certificate removed as well. And you can think of anything, any honestly benign reason for revoking the certificate. Even sometimes the requester themselves are going to send a message asking for certificate revocation, right? This whole thing is in need of being kept secure. For example, if attacker steals a user's private key, they could impersonate the victim by using digital certificates without other user being aware of the implementation, right? And this basically is going to cause, again, removal of integrity from this encryption method. In addition, think about what would happen if digital certificates were stolen from the CA, like that the storage that they discussed, the CR, is actually physically stolen, or a copy of it is taken and moved outside and shared in the dark web, right? The thieves could issue certificates to themselves that would be trusted by unsuspecting users. They go to their Bank of America while they actually are landing and the web page that the malicious actor is providing. The CA must publish list of approved certificates as well as revoked certificates in a timely fashion so that the security is not compromised. And that's what a CA is responsible to do periodically. And later we're going to see a screenshot on how you can check that on your computer to see a certificate is valid or is invalid. The status of a certificate can be checked in two ways to see if it has been revoked. The first is to use a certificate revocation list or a CRL, right? A CRL basically is a list of certificate serial numbers that have been revoked. And therefore, just looking at that list, you can know if the certificate is valid or not. Many CAs maintain an online CRL that can be queried by entering the certificate serial number or other information associated with the certificate. In addition, a local computer, and let me just go here so you can see the screenshot, a local computer can receive updates on the status of certificates and maintain a local CRL, as you can see here. In this case, the intermediate certificate authorities, you can go to certificates here and see a list of all the certificates that are valid or invalid because those are actually revoked. The second method is Online Certificate Status Protocol, or OCSP, which performs a real-time lookup of a certificate's status. OCSP is called the Request Response Protocol. The browser sends the certificate's information to a trusted entity like a CA server, which in that case, we call it the OCSP responder. The OCSP responder then provides revocation information on that one specific certificate which the query is about. And a variation of the OCSP that we are going to look into very soon in the next slide is called OCSP stabling. OCSP itself requires the OCSP responder to provide the responses to every web client of a certificate in real time, which may create a high volume of traffic. With OCSP stapling, web servers and queries to the responder OCSP server at regular intervals are being sent, and then they receive assigned timestamps or OCSP. Like if you look at here, the requests are being sent like on a regular basis. So when a client's web browser attempts to connect to the web server, the server can include, or in this case, we call it a staple, right? The handshake. So the handshake is stapled or includes with the web browser, and the previously received OCSP response is going to be attached there. So you can see as of this specific timestamp, the certification has been valid, or even worse, it hasn't been valid or it has been revoked in that case. So basically, the web browser sends the request, I want to connect. The web server sends the request to the OCSP responder, is the certificate valid? And then OCSP responds back, yes, here is the signed approval, which in that case is going to be stapled to this response that goes back to the web browser. This way, we're kind of like, let's say, saving the time that needs to happen with sending these requests on every second. So let's talk a little bit about the type of the certificates, right? So digital certificates can be grouped into the broad categories of root certificates, domain certificates, and hardware and software certificates. In addition, there are standardized certificate formats and attributes, which we're going to talk more as we go through this lecture. So first and foremost, root digital certificates. So in our example, Alice and Bob, right? Suppose that Alice is making a purchase at an online e-commerce site and needs to enter her credit card number. How can she be certain that she's at the authentic website of the retailer and not an imposter's lookalike site that has been sent the link to them through a phishing email, all these phishing emails that come in, right? And you look at that. The solution to that is a digital certificate. The online retailer's web server issues to Alice's web server on their computer a digital certificate that has been signed by a trusted third party. And this way, Alice can rest assured that she's at the authentic online retailer site and not on a phishing website. However, an estimated almost like 500,000 e-commerce sites that are in operation, and this is just my rough, let's say, recollection of the status that I have seen last year. So by now it should be even more than that. In addition, we have to consider the number of websites for banks, credit card companies, schools, workplaces, and many more websites that they all need to provide protection to their customers and clients. The question is, how can each digital certificate be verified as being authentic and not expired or revoked? And how should they be organized? This is going to be a super duper cumbersome job, right? So grouping and verifying digital certificates basically relies on certificate chaining. Certificate chaining creates a path between the trusted root CA. So you're going to have a root CA, as you can actually see over here, right? The Equifax in this case, right? And that has the original certificate. And there is going to be a trusted path to all the other intermediate CAs. So the beginning point of the chain is a specific type of digital certificate known as root digital certificate, in this case for Equifax. A root digital certificate is created and verified by a CA. Because a CA has no higher level authority, root digital certificates are self-signed and do not depend upon a higher level authority in authentication. The next level down from the root digital certificate is one or more intermediate certificate that you can see, like the GeoTrust Global CA or GeoTrust SSL CA GA. These are the intermediate next levels that are inheriting it, and now their trust is relying on the previous step. So the first step here at the root is self-signed, and then every single one of these is trusting the previous loop of the chain. And this is how the approved root digital certificate and intermediate certificates get distributed in a infrastructure for encryption. The distribution, however, can happen in three ways. First, they can be distributed through updates to the operating system. Second, they can be distributed through updates to the web browser. At one time, browsers relied on the underlying OS approved list, but today they rely on their own browser updates, right? So either OS or browser, and web browser certificates chaining that we have and the root digital certificates can be seen in browsers and are illustrated easily if you go right click on the properties of your browser, go to the setting and go to the certificates. You can easily see those in there and you can see who is providing the certificates to you. Most digital certificates are web server digital certificates that are issued from a web server to an endpoint, and this happens directly. Web server digital certificates perform two primary functions. They ensure the authenticity of the web server to the client and the authenticity of the cryptographic connection to the web server. Web servers can set up secure cryptographic connections by providing the server's public key with a digital certificate to the client. the handshake setup between web browser and web server that we also call it the key exchange, and we're going to discuss it a little bit more, is actually shown right here. This is what we call a key exchange. Let's go through these steps one by one and discuss what's going on there. So first and foremost, the web browser sends a message, which is like client hello, to the server that contains information, including the list of cryptographic algorithms that the client supports. On the next step, or server hello, the web server responds server hello by indicating which cryptographic algorithm will be used. So now the client, the web browser, knows what algorithm to use. It then sends the server digital certificate to the browser. Next step is the web browser verifies the server certificate, such as making sure it has not expired, it has not been revoked and so, and extracts the server's public key out of the certificate. The browser generates a random value, which we call it the pre-master secret, encrypt it with the server's public key, and then sends it back to the server, which in this case we call it client key exchange. Finally, the server decrypts the message and obtains the browser's pre-master secrets. Because both the browser and server now have the same pre-master secret, they can each create the same master secret off of it. And then the master secret is used to create session keys, which are symmetric keys to encrypt and decrypt information. These are exchanged during the session and then to verify the integrity of the communication. So as you can notice is the key exchange happens through asymmetric, and then after the key exchange is happening, everything switches back to symmetric. So some entry-level certificates provide domain-only validation to authenticate that only a specific organization has the right to use a particular domain name. A domain validation digital certificate, as you can see it down here, verifies the identity of the entity that has control over the domain name. The certificates indicate nothing regarding the trustworthiness of the individuals behind the site. They simply verify who controls the domain. So nobody else can actually control a domain that you have registered. An enhanced type of domain digital certificate is called Extended Validation Certificate, or EV. This type of certificate requires more extensive verification of the legitimacy of the business. Requirements usually include that the intermediate CA must pass an independent audit and verify that that the domain is really following all the EV standards. The existence and identity of the website owner, including the legal existence, physical existence, or maybe even asking for their IDs and all that, it's going to be done. So most of the time they need to show themselves to the authentication authority and get authenticated. The intermediate CA must also verify that the website is the registered holder and has exclusive control of the domain name. And finally, the authorization of the individuals applying for the certificate must be verified by the intermediate CA, and the valid signature from an officer of the company or the CA or the root CA even must be completed to finalize that application. So if you think about, and I'd like to kind of like quickly touch on the SAN and the wildcard before we go any further, so that you guys have information about those as well. A wildcard digital certificate is used to validate a main domain along with all subdomains. Like, for example, domain validation digital certificate for www.yahoo.com would only cover that specific site of yahoo.com. A wildcard digital certificate for asterisk.yahoo.com would cover every subdomain like mail.yahoo.com, news.yahoo.com, and such. So these certificates, the wildcard certificates, are covering a domain and all the possible subdomains. And then we do have the subject alternative name or SAN. Don't confuse this with storage area network, which is abbreviated as SAN as well. They also call it Unified Communications Certificate, UCC. Just for the sake of not getting confused with storage area network, I always recommend to use UCC rather than SAN. And UCC basically is primarily used for Microsoft Exchange servers or unified communications such as email or SMS or fax. This type of certificate allows multiple servers or domain names to use the same secure certificate by associating different values with the certificate. So basically, that's going to be an Exchange server. Multiple companies are using the same Exchange server, or one company is using that Exchange server just to provide multiple services like email, calendar, SharePoint, and stuff like that. Okay, now let's talk a bit about different type of attributes of formats that you can get on the digital certificates. Hardware devices require that digital certificates contain specific attributes, which are basically the fields and the certificate. And those are represented in a specific format. So every single hardware certificate must follow that. Doing so allows the device to read and process the digital certificate. The standard format for digital certificates is X509. The format was first introduced, I'm not sure, like years ago. I remember when I started learning computer, X509 was called an old format. So maybe 20, 30 years ago, but just know that's very old, right? And despite that, it was initially adopted for internet use, like internet was using X509 certificates since day one. The current version of it is version 3. Digital certificates following this standard can be read or written by any hardware device or application that follows X509 format. Several certificate attributes make up X509 digital certificate. These are used when parties negotiate a secure connection. Attributes that must be included are the certificate validity period, the end host identity information, encryption key, and on top of it, the signature of the issuing CA and the common name or CN, right? So multiple attributes are getting involved in order to make up 509. CN is the name of the device protected by the digital certificate. The CN can reference a single device like www.yahoo.com or multiple devices using a wildcard, right? So no matter what exactly is being used, or if you just want to use a wildcard and associate every subdomain. Using a wildcard is good if the entity is focused on providing multiple type of services, but otherwise it's not really recommended that much. X509 certificates can either be contained in a binary file, which is the file name .cer, so the extension of the file is .cer, or in a base 64 file, which is a binary to text encoding schema that presents binary data in ASCII string format. X509 certificates have 3 different encoding formats, or let's call them layouts, right? Basic encoding rules, or BER, canonical encoding rules, or CER, and distinguished encoding rules, or DER. So nowadays you can find the different type of these in different implementations out there. And this is an example on how you can actually use your browser and go to the properties of your certificate to be able to see X509 properties that you have in your public key over there. At this point, as you can see, they're using RSA 2048 bits, which is pretty strong. We talked a lot about asynchronous certificates. Let's stop and do a knowledge review. See who can help me answering this. Which of the following is the beginning point of a certificate chain? So we're talking about the point that self-signs. Remember, we said there is a point that starts everything. It is self-signed. B,
C.
C. Anybody else has any ideas?
I would say C as well.
Yeah, the survey says C as well, right? The beginning point, and let me just go back there. We're talking about this one, right? The beginning point is always the root. And the next intermediate certificate is basically relying on the root, and the second is relying on the first, and third is relying on the second, and so on and so forth. So that is called what? The chain of the trust, right? And we create the chain of the trust so that we don't need to go through verification step on every single item that we are encrypting or decrypting, and anytime we're doing that. So this was the first half of this discussion, right? The second half is talking about the PKI, which you most possibly have heard a lot about PKI so far. One of the important management tools for the use of digital certificate and asymmetric cryptography is the PKI, or public key infrastructure. You should understand public key infrastructure, know the PKI trust models and how the PKI is managed, and the features of the key management in order to say you understand the PKI. So one single digital certificate that we discussed in our example between Alice and Bob involves multiple entities and technologies. Asymmetric cryptography must be used to create the public and private keys. A registration authority must verify the CSR, and intermediate CA must process the CSR. The digital certificate must be placed in a CR, right? I'm using the abbreviations just to kind of like refresh your mind, right? All of these are what we already discussed. And after it is placed in CR, which is a certificate repository, should be moved to a CRL when it expires, and so on. In an organization where multiple users have digital certificates, and sometimes multiple digital certificates per user, to be honest, it can quickly become overwhelming for someone to manage all of these entities. In short, organizations need a consistent means to manage digital certificates, and PKI is what comes to rescue. So PKI is what you might expect from its name. It is the underlying infrastructure for key management of public keys and digital certificates. PKI is a framework for the administration of all the elements involved in digital certificates for digital certificate management, including hardware, software, even HR, people, right? Policies, procedures, standards, everything. And what it does for you is it creates, stores, distributes, and revokes digital certificates. So we can say, in short, it is like a one-stop shop for everything that you need for key infrastructure management. PKI works based on the trust models, right? Trust is identified as confidence in or actually reliance on another person or entity. One of the principal foundations of PKI is that of trust. Like in our example, Alice must trust that the public key in Bob's digital certificate belongs to Bob, and that trust should happen. A trust model refers to the type of trust relationship that can exist between individual or between entities. In one type of trust model, as you can see there, we do have the direct trust. It is a relationship that exists between two individuals because one person knows the other person, and the trust happens in there. Because in our example, for say, Alice knows Bob, she has seen him, she has worked with him, she recognizes him in a crowd or such. She has spoken with him actually multiple times. She can trust that the digital certificate that Bob personally give her for his public key is acceptable. But in the internet world, how often can we do this? How often can we see the person in person and actually trust them directly? It's almost impossible, right? Most of the communications we do over the internet happens between the parties that they have never seen each other. Good example is this classroom. Me and you guys have never seen each other in person. We just attend this class, so we cannot have a direct trust. A third-party trust refers to a situation in which two individuals trust each other because each trusts a common third party, like the example I used at the beginning of the class. An example of a third-party trust is a courtroom, right? Although the defendant and the prosecutor may not trust one another, they both can trust the judge, which is a third party, as a fair and impartial person. In this case, they implicitly trust each other because they share a common relationship with the judge. In terms of PKI, if our Alice example does not know Bob, it does not mean that she can never trust his digital certificate. Instead, if she trusts a third-party entity who Bob knows and they know Bob, right, then she can trust that the digital certificate with the public key that Bob is sending is trustworthy. A less secure trust model that uses no third party is called the web of trust model and is based on direct trust. Each user signs a digital certificate and then exchanges certificates with all other users. Because all users trust each other, each user can sign the certificate for all the other users. But in reality, if you want to go with such trust model, the problem you're going to have in internet is within a fraction of a second, everybody trusts everyone in internet, including all the malicious actors. So 3 PKI trust models use a CA, the hierarchical trust model, the distributed trust model, and the bridge trust model, which we want to discuss about them a little bit more. The hierarchical trust model assigns a single hierarchy with one master CA called the root. The root signs all digital certificate authorities with just one single key. This model can be used in an organization where one CA is responsible for only the digital certificates for all the organization. And the question should be like, hey, can one CA just sign that for everybody in the organization? Is that going to be a safe practice? What if that just one CA gets compromised? Everything in that case is going to be compromised because that one CA now turns into a single point of failure. However, on a larger scale, a hierarchical trust model has several limitations. First, if the CA's single private key were compromised, then all digital certificates would be worthless. Also, having single CA who must verify and sign all digital certificates may create a significant bottleneck or a backlog. So everything needs to go through that one CA, and that one CA is going to be super busy at all the times. So instead of having a single CA, like what we just discussed in a hierarchical trust model, the distributed trust model has multiple CAs that sign digital certificates. This essentially eliminates the limitations of hierarchical trust model. The loss of CA's private key would compromise only those digital certificates it had signed, not the rest that actually were signed by the other CAs. And the bottleneck is not going to happen because you have multiple signing authorities. So you can do load balancing between these multiple signing authorities, and therefore you can actually address both shortcomings of hierarchical trust model. However, do not forget that still with compromising any of these CAs, you're going to have compromised certificates in the network, which may be critical at the same time. It all depends on the impact, right? Remember, when we calculate the risk, we calculate the likelihood and we multiply that by the impact on the organization. So if you have one single certificate loss, which is belonging to the highest level of access and privilege in the network, then the impact of it is going to be way worse. And the risk of it is going to be way worse than having multiple certificates lost, which have a very minimal impact. Let's say for normal clerks that they just print out stuff. That's a different story, right? So always have the impact in mind. So the bridge trust model is really similar to the distributed trust model in that no single CA signs digital certificate. However, with the bridge trust model, one CA acts as a facilitator to interconnect all the other CAs. The facilitator CA does not himself issue any digital certificate. Instead, it acts as a hub between hierarchical trust model and distributed trust models, linking the models together basically, right? So in the bridge trust model, you are using multiple models within the same entity, within the same, let's say, enterprise, and then the bridge CA, the only thing that it does is just connects your different models and makes sure you have transient trust between different members of the models. An organization that uses multiple digital certificates on a regular basis needs to properly manage those digital certificates. Effective management includes establishing policies and practices and guidelines and determining the life cycle of digital certificates so that they can be revoked as they're not valid anymore. A CP, or a certificate policy, is a published set of rules that govern the operation of a PKI. The CP provides recommended baseline security requirements for the use and operation of a CA, intermediate CA, and other PKI components. A CP should cover such topics as CA or intermediate CA obligations, user obligations, confidentiality, operational requirements, and even training. A certificate practice statements, or CPS, is a more technical document than a CP. A CPS describes in detail how the CA uses and manages certificates. Additional topics for a CPS include how users register for a digital certificate, how to issue a digital certificate, when to revoke digital certificate, what makes a digital certificate obsolete, procedural controls, key pair generation and installation, and private key protection. X509 certificates contain a specific field that can link to the associated CP. In addition, extensions may be added to X509 certificates that indicate how the certificate should be used. One such field, like extended key usage field, can contain the object identifier that we call it OID, right? Which names the object or entity for further management. There are many details associated with X509 that take advantage of the existence of a CP. So let's talk about certification lifecycle. So far, we talked about how to manage it, how to create it. Now is the time that, okay, what is the whole life cycle? Digital certificates do not last forever. We all know that. Employees leave, new hardware is installed, applications are updated, cryptographic standards evolve, new technologies come out, and each change affects the usefulness of the digital certificate. Actually, one of the biggest contributors to these changes, the digital certificates and their security will be compromised by bad actors. And that is going to turn into a known vulnerability. The life cycle of a certificate is typically divided into 4 parts, starting with creation, at which stage the certificate is created and issued to the user. Before the digital certificate is generated, the user must be positively identified, as we discussed. The extent to which the user's identification must be confirmed can vary depending upon the type of certificate and any existing security policies depending on the enterprise. Once the user's identification has been verified, then the request is sent to the CA for a digital certificate. The CA can then apply its appropriate signing key to the certificate, effectively signing the public key, and then the relevant fields can be updated by the CA, and then the certificate will be forwarded to the registration authority. The CA also can keep a local copy of the certificate after it is being generated. So at the end of the day, a certificate once issued can be published to a public directory if necessary, so anyone else in the network can have access to that certificate. Next is suspension. In this stage, which could occur once or multiple times throughout the life of a digital certificate, and it all depends on certificate's validity, which can be temporarily suspended or indefinitely suspended. Suspension may occur, for example, when employees are on a leave of absence, on a maternity leave, anything like that, and their digital certificates may not be used for any reason until they return. Upon a user's return, the suspension can be withdrawn or the certificate can be completely revoked. Then next is revocation. At this stage, the certificate is no longer valid. Under certain situations, a certificate may be revoked before its normal expiration date, which is the next step that we're going to discuss. Some of these examples are like when user's private key is lost or compromised. When digital certificate is revoked, the CA updates its internal records and any CRL with the required certificate information and timestamp is going to be generated. Remember, if revoked certificate is identified in a CRL by its certificate serial number, we discussed how to look it up and we looked at the screenshot of the page. So anytime that certification is revoked, the CRL is going to be updated. The CA signs the CRL and then places it in a public repository so that other applications using this type of certificates can access the repository to determine the status of the certificate. Like if you have a disgruntled employee that is leaving the company, you want to revoke their certificate so that anytime they attempt accessing the systems, their certificate can be compared with the CRL, and upon existence in CRL, the disgruntled employee is going to be prohibited from conducting any malicious activity. Finally, we arrive at the expiration. At the expiration stage, the certificate can no longer be used. It's different from revocation, right? Revocation can be reversed, but at expiration, there is no reversing. Once it has expired, the certificate may not be used for any type of authentication. The user will be required to follow a process to receive a new certificate with a new expiration date. So the whole life cycle is in there to maintain the keys and make sure the integrity of encryption is intact. One common vulnerability that allows bad actors to compromise a PKI is improper certification and key management. Because keys from the foundation, because keys are actually the main foundation of the PKI system, they must be carefully managed. Proper key management includes key storage, key usage, and key handling procedures. The means of storing keys in a PKI system is super important. Public keys can be stored by embedding them with a digital certificate, while private keys can be stored on a user's local system. The drawback to software-based storage is that it can leave keys open to attacks. Vulnerabilities in the client operating system, for example, or even the applications on the client system can expose keys to the attackers. Storing keys in hardware is an alternative to software-based storage. For storing public keys, special CA root and intermediate CA hardware devices can be used, and private keys can be stored on smart cards, tokens, USB flash drives, RSAs, and such. If more security is needed than a single set of public and private keys, multiple pairs of dual keys can be created. One pair of keys may be used to encrypt information, and the public key can be backed up to another location. The second pair would be used only for digital signature, and the public key in the pair would never be backed up. Certain procedures can help ensuring the keys are properly handled. Some of them are key escrowing, right? First of all, let's stop and see if anybody has a question. Okay, cool. I assume not. So I hope I'm not going too fast, guys. So let's talk about the procedures that can help ensuring the proper handling and management of the keys. First, scroll. So key escrow refers to a procedure and a process in which keys are managed by a third party. So you escrow them to a third party, such as a trusted CA. In key escrow, the private key is split and each half is encrypted separately. The two halves are registered and sent to the third party, which stores each half in a separate location. A user can then retrieve the two halves, combine them, and use the new copy of the private key for decryption. Key escrow actually relieves users from worrying about losing their private keys. The drawback to the system, though, is that after a user has retrieved the two halves of the key and combined them to create a copy of the key, that copy of the key can be vulnerable to the attacks now. Next mechanism is expiration. Keys have an expiration date after which they cease to function. This prevents an attacker who may have stolen a private key from being able to decrypt the message for an unidentified or identified period. Some systems set keys to expire after a set period and default. So let's say after 24 hours. Next mechanism is renewal. So instead of letting a key expire and then creating a new key, an existing key can be renewed. With renewal, the original public and private keys can continue to be used, and new keys do not have to be generated. However, continually renewing keys makes them more vulnerable to theft or misuse, because if the key is stolen and even after expiration, you renew them, now the stolen key can be used again. Other mechanism is revocation. Whereas all keys should expire after a set period, a key may need to be revoked prior to its expiration date. For example, the need for revoking a key may be the result of an employee being terminated from his position. Revoked keys cannot be reinstated. The CA should be immediately notified when a key is revoked, and then the status of the key should be entered on the CRL. Next mechanism is recovery. So what happens if employees are hospitalized and their organization needs to transact business using their keys? Some CA systems have an embedded key recovery system that designates a key recovery agent. They call it a KRA, a highly trusted person responsible for recovering lost or damaged digital certificates. Digital certificates can be archived along with the user's private key. If the user is unavailable or if the certificate is lost, the certificate with the private key can be revoked and then can be recovered. Another technique is used, and they're calling it M of N control, in which a user's private key is encrypted and divided into a specific number of parts, such as, let's say, 3 or 4. The parts are distributed to other individuals with an overlap, so multiple individuals have the same part. For example, the 3 parts could be distributed to 6 people, with 2 people each having the same parts. This is known as the N group. And if it is necessary to recover the key, a smaller subset of the group needs to get involved in recovery. If a majority of the M group can agree, then they can piece the key together. However, we don't want to go very deep into different methods here, right? Just understand that the recovery is possible, and the simplest example of that, as we said, is okay, an employee has left, they're on maternity leave, and now we need to gain access to the files they have encrypted. So we need to recover their key to, let's say, the CEO of the company. So now the CEO of the company can look into the record and take care of what needs to be taken care of. Next mechanism is suspension. The revocation of a key is permanent. Key suspension is for set period. So instead of revoking, we're just suspending it. And then finally, destruction. Key destruction removes all private and public keys along with the user's identification information in the CA. No more record of that. When a key is revoked or expires, the user's information remains on the CA for audit purposes. So we never really just go ahead and delete everything. Let's stop and do another knowledge review. So which of the following is considered a non-secure place where PKI encryption keys may be stored?
C.
D, local system.
Any other ideas? Okay, so the survey says D, local system. And then remember, choosing the C in a digital certificate is not considered unsafe. Of course, it can be broken. Anything can be broken. Like in security, we have nothing that provides 100% security. But if you want to compare these options, having it on a local system makes it prone to any kind of attack on that system and therefore loss of information on that system. Okay, now what we want to do for the rest is talking about common cryptographic transport algorithms, right? Starting with secure socket layer or SSL. This one, first of all, let me ask you guys, do you know how HTTP protocol can be secured to HTTPS? Anyone has idea on that? The answer is in front of you, using the SSL protocol, right? So it was one of the early and most widespread cryptographic protocols, and it's called Secure Socket Layer or SSL. The protocol was developed by Netscape in 1994, as you can see on the slide. It's good that I have these written, otherwise I wouldn't be able to remember that number. It was developed in a response to the growing concern over internet security. The design goal of SSL was to create an encrypted data path between a client, in this case a browser, right, and a server, which is a service, which could be used on any platform or operating system. The current version of SSL is 3.0. However, the way SSL function has left it vulnerable to attack made everybody concerned. When the user arrives on a secure web page via a link from a non-secure site, the sequence that happens is the user's browser sends an unsecure HTTP request to the web server, and then the server responds via HTTP and redirects the browser to a secure page, instructing it to use the secure protocol HTTPS. Then the user's browsers sends a secure HTTPS request and the secure session begins. A threat actor can intercept the new request for the user to the server. This basically is what we call a session hijacking. So an actor can stay aside, wait for the user to start the session, and when the session is authenticated, the actor can then do a middleman attack and take it over. Now this hijacked session can be used for unwanted activity. TLS, or Transport Layer Security, is a widespread cryptographic protocol that is the replacement for SSL. Although the algorithms SSL and TLS use more the same technology and the same type of algorithms, and they both are listed as being interchangeable or even linked to each other. Sometimes they're referred to as TLS/SSL. If you have set up your Outlook or mail client manually in the past, you have seen that you have to choose which one of these protocols are being used and what version of those. Although TLS version 1 was considered marginally more secure than SSL version 3, which is the higher level, and I mean the highest and more advanced level of SSL. However, TLS version 1 was also showing vulnerabilities, right? Then the subsequent versions were introduced and all that, and different cipher suits were actually introduced in order to fix the problem. A cipher suit is a named combination of the encryption, authentication, and message authentication code, or MAC. And again, look at all these abbreviations. And someone was asking me, do I need to memorize these applications and the abbreviations? And the answer is no way, because we even use them in a redundant fashion. Over here, the message authentication code, or MAC, Also, MAC is used for media access control or MAC address, and you have seen it in the past, right? So you really want to focus on the context rather than memorizing all of these abbreviations and such. Next one is a secure shell or SSH. SSH is an encrypted alternative to the Telnet protocol used to access remote computers. SSH is a Linux, Unix-based command interface and protocol for securely accessing remote computer. SSH is actually a suite of the three utilities: S-login or secure login to a remote computer, SSH, execute commands on a remote host without logging in, and SCP, copy files between remote computers. That are secure versions of the unsecure Unix counterpart utilities. Both the client and server, they authenticate using digital certificates. Actually, they also use passwords, right? So SSH can be used as a tool for secure network backups, as you see on the slide. One common use of TLS and the older SSL is to secure HTTP or hypertext transport protocol. When you use that, you're going to turn the plain HTTP, turning each into HTTPS. HTTPS uses port 443, while HTTP uses port 80 or port 8080. And what you can see to distinguish if that is HTTPS is in your browser, it starts with HTTPS rather than HTTP. Now we arrive at the mail protocols, right? Secure multipurpose internet mail extensions. SMIME is a protocol for securing email messages. It is a standard for how an electronic message will be organized. So the SMIME describes how encryption information and a digital certificate can be included as a part of the message body. It actually allows users to send encrypted messages that are also digitally signed. Again, we're going to discuss these protocols in more details. This is more like introduction to the protocols, and that's why I'm just giving you a brief explanation about each one. Then we do have the SRTP. The secure real-time transport protocol has several similarities to SMIME, just as SMIME is intended to protect MIME communications. SRTP is a secure extension protecting transmissions using the real-time transport protocol, or RTP. Also, as the previous protocol is designed to protect only email communications, SRTP provides protection for voice over IP or VoIP, and it adds security features such as message authentication and confidentiality for VoIP communications. Next to look at is IPsec. Internet Protocol Security is a protocol suite for securing Internet Protocol or IP communications. IPsec encrypts and authenticates each IP packet, and refresh your memory with the OSI model understanding that we had before, right? Each IP packet is encapsulated information with the tags that each layer adds to the header, and the payload is being protected through that encryption. So IPsec can provide protection to a much wider range of applications than TLS or the older SSL can do. So IPsec is considered a transport security protocol. It is transparent to applications, to users, and to softwares. So programs do not have to be modified to run under IPsec. You don't need to change anything. Unlike some security tools, users as well do not need to be trained on a specific security procedures, such as encrypting with PGP when it comes to IPsec. And again, because IPsec is implemented in a device, such a firewall or a router, no software changes must be made on the local client. Unlike TLS, which is implemented as a part of the user application, IPsec is in the operating system or the communication hardware. IPsec is more likely to operate at a faster speed because it can cooperate closely with other system programs and hardware. The IPsec itself provides 3 areas of protection that correspond to 3 IPsec protocols: authentication, confidentiality, and key management. For the authentication, IPsec authenticates that packets received were sent from the source. The authentication is identified in the header of the packet to ensure that no specific attacks took place to alter the contents of the packet. This is actually accomplished by the AH protocol, or authentication header protocol, which we're going to discuss it in the coming lectures. For the confidentiality, by encrypting the packets, IPsec ensures that no other parties could view the content. So confidentiality is achieved through the encapsulating security payload, or ESP protocol, which again, we're going to talk about it later. ESP itself supports authentication of the sender and encryption of the data. And finally, key management. IPsec manages the keys to ensure that they are not intercepted or used by unauthorized parties. For IPsec to work, the sending and receiving devices must share the key. This is accomplished through a protocol known as Internet Security Association and Key Management Protocol, Oakley, which again, we're going to talk about it later. IPsec supports 2 encryption modes: transport and tunnel. Transport mode encrypts only the data portion, which is called payload, of each packet, yet leaves the header unencrypted. The more secure tunnel protocol, or tunnel mode, encrypts both the header and the data portion. IPsec itself accomplishes transport and tunnel modes by adding new headers to the IP packets. And note that with adding new headers to the IP packet, you're actually making the packets larger, and therefore you're reducing the performance of the system. So there is always a drawback. Whenever you go to more security, you are removing availability. Please remember the triad of CIA, which we studied in the previous lectures. At first glance, it seems cryptographic protocols should have few, if any, weaknesses, since they are built upon well-known algorithms and everybody is aware of those. So any security issues with cryptographic protocols would also be equal to those issues within the cryptographic algorithms, right? However, that is not the case for multiple reasons that you can just look at it on this slide. Due to the inherent complexity of networking, cryptographic protocols are notoriously difficult to design. While the mathematics and related security of basic cryptographic algorithms have been extensively studied and are well understood, the same cannot always be said of cryptographic protocols. The critical analysis of these protocols has often not reached the same level of the cryptographic algorithms. Thus, cryptographic protocol errors and implementation errors in cryptographic protocols that have been in use for decades are still being uncovered. Several older cryptographic protocols still in use today were designed by networking experts and not by cryptographic protocol experts. As a result, a cryptographic protocol suffer more from legacy issues than underlying cryptographic algorithm weaknesses. The associated security proofs to guarantee the correctness of cryptographic protocols are much more complicated than those of cryptographic algorithms. So despite the fact that we agree that the weaknesses are there, but they're not necessarily as crazy as one would imagine with all of those errors, that cryptography is going to be super weak. Let's do a quick knowledge review. Which encryption protocol is used for securing email messages?
A.
Nice. So looks like you guys have been noticing that. The correct answer is A, as we discussed earlier. So let's talk about implementing cryptography. So cryptography is improperly applied in most of the cases. And if this happens, it can lead to vulnerabilities. So same way that it can secure the system, if improperly applied, it is going to make your system even less strong. So it is essential to understand the different options that relate to cryptography, and implementing cryptography needs the good understanding of key strength, secret algorithms, block cipher modes of operation, cryptographic service providers, and the use of algorithm input values. So when it comes to the key strengths, as we discussed, the cryptographic key is the value that serves as an input to an algorithm. So if this value is not strong enough, as this value is not large and long enough, it can easily be deciphered and easily be broken into by the bad actors. There are three primary characteristics that determine the resiliency of the key to attacks, and we call them key strength. The first is randomness. A key is considered strong when it is random with no predictable pattern. For example, your password, your key should not include your date of birth, right? A random key thwarts an attacker from attempting to uncover the key through basically just guessing what the key may be. The second characteristic that we want to discuss here is a crypto period, right? Or length of the key. So the crypto period is the time for which the key is authorized to be used. That is why you're being asked to change your passwords more often. So you want to keep the length short. So if the password gets compromised, you actually are able to recover from that, because then the password is going to be changed and the compromised password cannot be used anymore. Finally, we want to talk about the size of the key, right? How big the key is. The larger the key itself, the more difficult it is to be broken. And mathematically, it's proven the larger ones take more time and more processing in order to be broken into. So keys must be kept secret except for the public keys. Question is, does the same apply to algorithms? That is, should an enterprise invest in hiring a cryptographer to create a new cryptographic algorithm and then hide the existence of that algorithm from everyone? Wouldn't such a secret algorithm enhance security in the same way as keeping a key or secret or a password secret? Of course, the answer is no. In the past, cryptographers have often attempted to keep their algorithms or the workings of devices that encrypted and decrypted documents a secret. However, the approach has always failed. One reason is that cryptography is the most useful when it is widespread. A military force that uses cryptography must by nature allow many users to know of its existence to use it. Otherwise, why is the algorithm out there to begin with? The more users who know about it, the more difficult it is to keep it a secret. In contrast, a password only requires one person, which is the user, to keep it confidential. One variation in cryptographic algorithms is the amount of data that is processed at a time. Some algorithms use a stream cipher, while other algorithms make use of a block cipher, whereas a stream cipher works on one character at a time. A block cipher manipulates and can work on the entire block of plain text at one time. Because the size of this plain text is usually larger than the block size itself, the plain text is divided into separate blocks of specific lengths, and then each block is encrypted independently. A block cipher mode of operation specifies how block cipher should handle the blocks. It uses a symmetric key block cipher algorithm to provide an information service. The service could be authentication mode of operation that provides a credentialing service for authentication mode of operation that provides a service such as confidentiality, and it can go to the common modes like electronic code book or ECB, which is the most basic approach, honestly. The plain text is divided into blocks, and each block is then encrypted separately. However, this can result in two identical plain text blocks being encrypted into two identical cipher blocks, and attackers can use the repetition to their advantage. They could modify the encrypted message by modifying a block or even reshuffling the order of the blocks of cipher. So honestly, ECB is not considered suitable for use. It's old, not reliable. Cipher block chaining, or CBC, is a common cipher mode. After being encrypted, each ciphertext block gets fed back and goes back to the encryption process to encrypt the next plaintext block. Using CBC, each block of plain text is XORed with the previous block of ciphertext before being encrypted. Unlike ECB, in which the ciphertext depends only upon a plain text and the key, CBC is also dependent on the previous cipher block, making it way more difficult to be broken into. Counter mode requires that both the message sender and receiver acts as a counter, which computes a new value each time a ciphertext block is exchanged. The weakness of CTR is that it requires a synchronous counter for both sender and receiver, which usually is a problem. GCM, or Gaulius counter, basically is a mode that both encrypts plain text and computes a message authentication code, or a MAC, to ensure that the message was created by the sender and that it was not tampered with during transmission. Like CTR, GCM uses a counter. It adds plain text string called additional authentication data, or AAD, to the transmission, and the AAD may contain the address and parameters of the network protocol that is being used. It makes it more complicated. At the same time, it has the same drawback in which it needs both sides, sender and receiver, have a timer. Finally, let's talk a bit about the crypto service provider. A crypto service provider allows an application to implement an encryption algorithm for execution. Typically, crypto service providers implement cryptographic algorithms, generate keys, provide key storage, and authenticate users by calling various crypto modules to perform the specific tasks. crypto service providers can be implemented in software, hardware, or both, and are often parts of operating systems. Operating systems have cryptographic services enabled and the providers may actually be created and distributed by third parties, allowing for a broader algorithm selection for data specific operating system. Let's do another knowledge check. Which of the following is not a primary characteristics of key strength?
Uniqueness.
Anyone else wants to answer that? So the correct answer is uniqueness, right? And we discussed it earlier on the top. So let's see what we did here. We discussed these points. A digital certificate is a user's public key that has been digitally signed by a trusted third party who verifies the owner, and that public key belongs to that owner. We discussed the CRs. We talked about the process of verifying the digital signatures and digital certificates. We talked about the domain validation and domain certificates. We discussed about the public key infrastructure. We talked about how organizations use multiple digital certificates to properly manage the digital certificates. We talked about cryptography as common use to protect data and for transmission and in motion. So basically, remember that everything that we discussed was about the data that moves between 2 points. We didn't discuss the data that is being stored on the drive. And finally, we said cryptography that is improperly applied can lead to vulnerabilities that will be exploited, and hence they're gonna turn into the issues themselves.